All right, everybody. Who was here earlier this morning for the opening ceremonies? Yeah, that was a really lively, great bunch, wasn't it? Um, myself included. So, as said, I am Lillian Ash Baker. I am one of the representatives and volunteers with the Aerospace Village. I also work for the Boeing Company as a product security engineer, and also a subsidiary of theirs, Whisk Aero, as the lead product security engineer for that product that we're building. Today, what I would really like to talk about is one of the most important parts of aircraft system development. Does anyone know what that is? No. It's standards and certification and safety. Those are the three main pieces for aircraft development. And what I hope for you to get out of this is something a little bit different than a lot of other talks. A lot of other talks are going to talk about how very specifically you can take some of this information and apply it into your own areas. What I'm talking about here is ideas that we use in aviation that you can use to augment your own processes and your own ways of thinking in order to better your systems development. So, first thing that we need to do is discuss safety and what safety is and what we actually mean by safety in a system, because every industry will have a little bit of a different take on what exactly safety is. In the aviation, it is a legal definition, and we'll get into that. So, I hope you all find this as interesting as I do. I still have not shut up about safety in aviation for the past 17 years. I think this is like one of the most important and interesting things about the industry. So, first principles of safety here. Safety classifications come from two documents, Part 23 and Part 25. Part 23 certification is general aviation aircraft under, I believe it's 16 passengers. Anything over that is Part 25. There's a very important reason why there's a distinguishing line between the two of those, and that's because the safety levels vary depending on the type of aircraft that you're actually developing. So with that, we have these failure conditions, these minor, major, hazardous, or severe major, which was added in as part of Part 23 and then adopted in Part 25 years later, and then catastrophic. And with that is these probabilities, right? So the way that safety works is that this is a probabilistic process that we have to take a look at that is quantitative and qualitative in nature. Now, this little graph over here off to the side is directly out of Part 25. That number up there, it's kind of hard to read. It says 6/21/88. Who was born after that date? Yeah, so the classifications for safety were around before you were born, right? This is stuff that has been around for almost 30 years at this point. It's very, 40 years. Again, I'm getting my own age a little bit mixed up. This is the bedrock of how civil aviation works and why it works so well. Because a lot of this information comes from a time period where a lot of people were killed in accidents repeatedly because aircraft failed, systems failed. So all of these regulations come from a time period that was created from blood. This is why it's so important for us to understand why these classifications are important. So I talked about the probabilities in this, and these are the numbers for probable that come from Part 25 and also Part 23. So minor probability is on the order of 10 to the minus 5, right? That's just for minor. Minor is basically some damage to the aircraft, but still usable. It's when we get down here to the catastrophic levels, which are extremely improbable, on the order of 10 to the minus 9th or less, which means that your system has to operate for approximately somewhere between 10,000 to 1 million hours without failure. Single failure. time before a single failure. This is something that no other industry really does in the same way. Now, this is also system level, right? So single LRUs, or line replaceable units, equipment that you put on board an aircraft, cannot have probabilities better than 10 to the minus fourth. And that also comes from a qualitative analysis. So you have to build a system of multiple pieces of equipment to even hit the single loss for functional level. So that might mean 3 systems can fail or have to fail in order to get to this catastrophic probability. Major got redefined as remote at some point. Hazardous came in because they needed something in between major at the 10 to the minus 9, or sorry, 5 to 9 range. So they put hazardous or severe, severe, extremely remote in between at 10 to the minus 7. And we'll get to what that actually means here in just a moment. With that comes this chart. So we have different classifications of the severity condition with the name over to what it actually means: improbable, extremely improbable, remote, or no safety effect, right? None. With the on the order of what the actual probabilities of that happening are. And that goes into the functional safety analysis or hazard analysis for system development. Then we get to this other area, which is the functional DAL assignments, A, B, C, D, and E. Design assurance levels are definitions for safety impacts as you develop equipment. So if the function that I'm developing, say it is the autopilot for an aircraft, the flight director, it's probably going to have DAL A, DAL B effects, which means when I do my analysis, that system cannot fail more often than this probability. And I have to ensure through my design assurance level and my design assurance processes that I can achieve that. Now, what's really, really cool about this is that we get into development objectives. So this is where we start to talk about the other letters that I was mentioned this morning: DO 178, DO 254, ARP 4754 for system development. And those DAL levels, A, B, C, D, and E, dictate exactly what you have to do in your development processes. So, development processes, it's not telling you how to do your development. It's telling you what you need to do in order to prove that you did the work to make your system safe. It's a very different approach to how this all works. With that comes paperwork. Lots of paperwork, ridiculous amounts of paperwork, and a lot of other work on top of all of that. If you start to get up into DAL, so this is actually SAL that I pulled the chart from for security assurance. But once you get up into DAL A, you start to see an R with a nice little star next to it. That star means that you have to have independence, which means that the person that writes code cannot be the person who verifies the code. You now have to have somebody else, either within your company, in a completely different organization, that does the verification of your code. It could be a contractor, it could be multiple other ways of achieving that. But the point is, the person who wrote the code cannot be the one that says the code does the functions that it's supposed to. That takes a lot of additional work, incredible amounts of additional work. It requires a lot of additional requirements work and all these other objectives to be met. But it's all in the name of making these systems as perfect as they can possibly be. Now, with that, we start to talk about how that ties into security a little bit more. So, shifting our perspective a little bit here. We're going to talk about DO356, which is security objectives for aviation systems, how you do your development, what sort of artifacts that you need to produce as part of your development process. And we have this really cool definition that comes up in DO356 called IUEI, unintentional, unauthorized electronic interactions. The concept there is that you have to prove that the interaction that you're having with your system was intentionally done by somebody. They did not have the authorization to do such a thing. It is electronic in nature, so that removes the physical security part of our conversation, because physical security is completely different than the electronic security for aviation systems, and that it had to have some interaction with those electronic systems on board. Now, what's really interesting about this is that you get kind of different questions that safety and security ask. Safety starts to ask questions about failure conditions of what happened and why did it happen? What led to that effect for the safety to be impacted on the system? Security looks at a completely different set of questions, the who and the where. Who was it that did the interaction, and what was the entry point into the system? Because one of the big differences with security and safety, safety looks at threads throughout a system. You have to ensure that the safety runs from originating system all the way over into the system that is actually using the data and presenting it to a pilot, or takes pilot input and moves an actuator back and forth. They don't look at intermediaries in between. That's all wrapped up into the functional hazard assessment. We already took that into consideration. Now, security, however, you can have multiple entry points to impact the safety of a system function at any point of the system. And that's a big difference that is made in this. So when we talk about the safety levels and the threat vectors to a system, we have to know exactly what the safety function is on that system and what the level is. And the reason is because we want to know how bad a hacker or some other unintentional user has impacted that system. And after we know that, we're then required to go put mitigations in place into the system. Now, what's a little bit different about safety or security side of things, safety just says you just develop your system until it's perfect. You just start adding stuff, you add in mitigation, or not mitigations, you add in safety effectors in order to bring the numbers up higher and higher. That might be cross-checking data. That might be having a third piece of data, a third data source to cross-check against. Might be in multiple different places. What's interesting is that when you get up to catastrophic, it has SAL 3+2, which goes back to our objectives of the system. SAL being security assurance level. 3+2 means that you have to have 2 mitigations for every attack vector. Now, what's really different about that is that it does not have to be in the same system. It can be spread out across multiple systems, as long as it has the ability of stopping that attack vector as it moves through a system. So it's a very different way of thinking about it, so that it takes pivoting into consideration as part of the attack vectors as well. With that, it also affects how you do your development. And what's really nice about it, and is not tied into this here, is that those security objectives for SAL 3, for SAL 2, SAL 1 actually have mappings over into the safety objectives for DAL A, DAL B, and DAL C. So you kind of get the assurance baked right into your development processes if you're following the development processes right. The other piece that's really interesting is that if you do your analysis and you say that, look, my analysis does not take into account the actual criticality of this system, be it maintenance systems, Maintenance systems are typically very low-level DAL-D systems, but they can have high impacts to a system. So you have the ability to actually raise the security level and say, I'm raising the security level of that function, and apply it across your system. It's a very different way than how safety approaches the problem by saying like, nope, the analysis shows that it's good, it's good. And it also kind of shows where safety or security needs to mature a little bit more to take those into account for the threat vectors and the analyses that are going on. And if you look down here at the assurance levels as well, it gives some definitions behind this. So it says SAL 3 is strongest security assurance for security measures. It really ties back to that design assurance piece of it as well. All right. So what I would like to do is I would actually like to walk through a sample system, right? We can't sit here and talk about how we do system analysis and how you throw all these numbers and letters through. So we're actually going to walk through a system thread. So in this case, in this example, our functional hazard assessment says that this system thread is a DAL-B system, right? So the data as it goes from system A to system B to system C out to the user display has a hazard level of 10 to the minus 7, okay? Which means if there's any threat vectors, we have to have SAL 2 mitigations in place. Safety analyses are very much a linear top-down look at a system from first entry point of data into a system all the way out to the endpoint user. So in this case being the user display. So let's take a look. So we do an analysis here and we apply safety requirements. There was an analysis done. The FHA came back and said, these are the requirements that we have to put in place of our system in totality. So we're going to monitor failures and enunciate in system A. We are going to check the validity of the input on system B, which takes an input, adds 2, and outputs the data. We're then also going to check the validity of input into system C. Cool. Our system now meets DAL-B by all of our analysis. Oh. So the cyber team went through and started looking at the system, and they found on system B that an attack could actually modify the inputs or the code in that area, and now it can modify the output of that system. That's not good. We now show that an attack in the middle of the system can impact erroneous data to the user display, impacting the DAL-B functionality of that system. Okay, not a problem. We can get through this. Okay, we can do memory hashing. Cool. So now we took care of the problem. We hash the memory space. We know when there's going to be an attack that happens. We also added in a secondary system on system B so that we could do cross-checking of that data so that we know that if one system gets impacted, we can always check a second independent system and see that it's not being impacted. Except our cyber team also found that they could shut down the interface by flooding system C with junk data. And now no data goes into this, impacting the function of the unit of the system again. Okay, so we put in some DDoS protections. Everything's great. This time, they figured out that they can set a mode command which back propagates into system B and goes all the way back to system A, switches the mode of the system, which then forward propagates back through the system and changing modes of that data without the user ever knowing on the user display. But part of that was also that system C sent it down the system B prime pipeline on the cross side and also commanded it to do it. So all that cross-checking that we did, it doesn't matter because both systems are now in the same mode. So this example is to show you that there's all these different areas where safety and security touch, right? Memory hashing is something that you typically do for the safety of a system, right? You want to ensure that no sort of environmental effects change the memory spaces. So you hash them and you rehash them and you copy that hash into a third memory space, and then you pull that in. And then when it's wrong, you pull a secondary copy. And when that one's wrong, you pull the third copy. And if it's wrong again, you throw the whole system away. But also, it helps protect the security of the system, right? We added a security requirement that said hash the memory spaces. So in this example, we can put in requirements that could either be a safety requirement or a safety requirement and increase the other one's overall safety or security levels. If I put it in for security, it improves the safety of the system. Likewise, for having this secondary system with DDoS protections, I put in a very specific security implementation that has safety implications as well. Because if that system now sees that there's an attempted DDoS attack on that interface, guess what it's going to do? It's going to cut off all interfaces, which means I no longer have safety data, safety critical data going to the user display. I've cut it off. I've stopped it from going. In this case, the DDoS protection has now reduced the amount of safety in the system. So, in summary, aircraft cybersecurity is still a very young discipline. DO356 was only released in 2014. It's not that long ago. But it has had the rest of the cybersecurity industry in order to grow upon. If you go look at 356, one of the really cool things about it is that it has a references table that has all sorts of information in there for other sources like NIST 160, 800, 160, 853, et cetera, et cetera, et cetera. It's built upon the rest of the cybersecurity industry. And as we kind of discussed earlier this morning, the connectivity with aircraft has now increased and keeps increasing with every successive generation of aircraft. At the same time, we're taking away federated systems and putting multiple functions together into a single system. And so with this, it presents more opportunities for cyber attacks to become worse and worse. So in short, the only truly cyber safe system or safe system has to be a cyber secure system.
We do have some time for Q&A. If anybody has any questions, please let us know here. Any questions? You might get off the hook here.
I might. One question.
Oh. Sorry about that. No, all right, just one quick question. So as we progress forward in the future, right, and we start to look at autonomous flying of airplanes, right?
Sure.
Do we expect there to be like a massive pull for kind of standardizations across all aircraft, both human piloted and drone?
Yeah, so that's actually a really interesting question. So there's actually two roads that have developed. Here in the US, we develop our UAM, that's urban air mobility aircraft, to be under Part 23. So just as your Cessnas, just as your Cirruses, just as your small aircraft, they get developed under Part 23. And so they fall under yet another standard, ASTM F3532-22, which also gives you a backdoor to start using 326 and 356 as well. Europe is going a little bit in a different direction. And what happened in Europe with EuroK is there's an organization of eVTOL manufacturers and groups that got together and they started their own cybersecurity standard, ED 305. Now, the interesting thing about ED 305 is that none of the working members from RTCA SC 216 or EuroK Working Group 76 actually worked on that standard. Someone else not involved with the Part 25 security worked on that standard. And it completely has a different look on the safety security levels and impacts. It's very different. So there's there's a little bit of market play happening going back and forth. The problem is that we start to get into reciprocity issues between the FAA and Euro and EASA, where they try to be the same as much as possible. And this is one area where like the link is definitely broken.
Any other questions? Thanks for ending it on a downer.
Yeah, absolutely.